Hi everyone, I'm Signe Rüsch from TU Braunschweig, Germany, and I want to present our work ZugChain, blockchain-based juridical data recording in railway systems for DSN 2022. This work is part of the RailChain project in collaboration with Siemens Mobility, Siemens, the Hasso-Plattner-Institute, DB System, and the University of Stavanger, Norway. Modern trains are equipped with a black box, a so-called juridical recording unit, which, as the name suggests, records all juridically relevant data. This can be the current speed and location of the train, any brake activity, doors opening or closing, and all with corresponding timestamps. This data that has to be logged is received via bus communication, and it is used to detect malfunctions. For example, after an accident, it is used in root cause analysis to determine the cause of this accident. The device of the JRU is especially hardened, meaning it is built to withstand physical damage, for example in the case of fire or impact. However, there are some problems with the current JRU approach. As there's only one JRU per train, it could become a single point of failure, meaning that in the case of an accident, we could potentially lose data. For example, it is possible for the JRU to become destroyed in a crash, even though it is an especially hardened device. And it has been shown in the past that data can become manipulated during the extraction process. The data extraction is a complex and time-consuming process. During operational pauses, an employee has to access the JRU with a physical key in order to unlock the USB port, here as shown on the right, and there is currently no option to remotely extract the data or to export it during train operation. The JRU is also an expensive and proprietary device, meaning that only one company, namely the company that built the JRU, has authority over this juridical logging. And there is no distribution of trust amongst, for example, all the other companies that provide components for the train. Our goals in our project is therefore to replace the single device of the JRU with a distributed, replicated system. During this, we have to ensure to maintain the high reliability and availability of the traditional JRU, and we also have to ensure data integrity of our data logging. We also have to consider the cost factor. The JRU is an expensive, dedicated hardware device. In our approach, instead, we want to opportunistically use on-train commodity hardware, and we want to require no changes to the train's safety-critical infrastructure. Furthermore, we want to allow multiple companies to contribute to this juridical recording, so we want to have this distribution of trust. And lastly, we want to facilitate easy data export during train operation to enable new use cases, for example, predictive maintenance. If we want to distribute our juridical data logging, we first need to verify that we can reach the levels of reliability and availability as required for the JRU. And for this, we turn to the mathematical analysis by Brabant et al. From 2020, where the authors analyzed exactly this question: what is the reliability and availability of such a distributed JRU functionality running on commodity hardware? For this, they took train crash data from the recent years provided by the International Union of Railways and the European Union Agency for Railways, and determined certain probabilities for different scenarios. So, for example, whether the train catches on fire in case of an accident, or how much of the train becomes damaged by impact, and how does this affect the recording hardware. And the key findings were that, unsurprisingly, commodity hardware is easier to destroy than a specially hardened device such as the JRU. However, crashes rarely affect the whole train. So the authors concluded that if we distribute the JRU functionality across the whole train, we can reach comparable levels of reliability and availability even on commodity hardware. So that is good for us. However, the question still remains: how can we ensure that all of our distributed nodes log the same data and have a consistent state? We present ZugChain, a blockchain-based juridical data recorder for railway systems. The ZugChain nodes are opportunistically running on commodity hardware, shared with other functionalities, and can be provided by multiple companies, therefore sharing the logging authority. They are also distributed across the whole train. They read safety-critical, juridically relevant signals from the bus, and in the next step, agree on the received signals and log these signals in a private, permissioned blockchain maintained by the nodes. As the agreement should not congest the safety-critical bus link, consensus messages are exchanged via existing non-critical links, such as the Ethernet connection as shown below. The blockchain structure ensures data integrity and allows us to externally verify this data integrity, which is also an advantage for the export protocol we provide in order to externalize juridical recordings during train operation to the railway company's data center. We have considered several alternative approaches. A naive solution would be to simply place multiple independent JRUs on the train running in parallel. However, their logs would not be synchronized and they might have a differing view on the system, for example, if nodes do not all receive the complete data due to network problems. And this means that in case of a crash, this would require all nodes to be intact to get the complete picture or risk data loss. The second solution is a simple leader-follower approach. Here we only need one remaining node after a crash. However, data can still be compromised, either during operation or during export. The transmission between the nodes via the bus system might also become corrupted, leading to differing recordings. We therefore have to consider agreement between nodes on the received data. As we opportunistically use on-train hardware for ZugChain, the juridical recording functionality may actually be co-located with the observed system, and as we consider this observed system capable of arbitrary behavior, we have to ensure that this does not in any way influence the recording. Such arbitrary behavior can include dropping, reordering, duplicating, delaying, or corrupting messages, and this is true both for consensus messages as well as for data read from the bus. This leads to the conclusion that we need Byzantine agreement for ZugChain. However, in ZugChain we have a different setting than in traditional BFT systems. In traditional systems, as shown on the left, we have a client that sends authenticated requests either to the leader of the replication group or as a broadcast to the completed replication group, and replicas can forward requests amongst each other, for example to the correct leader. Also, a client can retransmit requests if it notices that its request has not been processed after a certain amount of time. In our system in the train, shown on the right, we receive input via time-triggered bus communication as an unauthenticated broadcast. The communication is synchronous, and it is possible that the replicas read differing data from the bus, for example due to bit flips. We therefore have to log all data received by any replica. We also cannot risk losing any requests. The signal source is not interested in response to its request as a traditional client is, and therefore won't retransmit the data if we don't log it. For this, we introduce the ZugChain communication layer. It encapsulates the underlying Byzantine agreement protocol, for example, the well-established PBFT protocol. And now, as we've just said, nodes can either read identical or diverging data from the bus. So we have to ensure that we record all data received by any node in the system. However, if we truly log all identical input, we would incur a large overhead due to the amount of duplicates in the normal operation. Our communication layer therefore ensures no payload duplication, meaning we still log all juridically relevant data, but we filter out any duplicates, any identical data, while at the same time preventing the omission of data. The communication layer works as follows. The ZugChain nodes generally assume that all other nodes read identical data, so that we are in the optimal case, and only the primary proposes the request that it has read from the bus, whereas the backups don't propose their request. However, the backups set a soft timer for each request that they read from the bus. And now if this soft timer expires before the node has received a matching pre-prepare for this request, then it broadcasts this request to all other nodes, assuming that it is the only node who has read this exact request, this exact data from the bus. It then starts a hard timer, and again, if it has not received a matching pre-prepare before this hard timer expires, then it starts the view change. And as all other replicas are also aware of this request after the broadcasting step and have forwarded it to the primary, they also assume that the primary is faulty and agree to the view change. Let's have a look at the export protocol. Storage on the train nodes is quite limited, and in general we are more interested in most recent data. So for example, if there's an accident, if the train crashes, we want to know what happened shortly before that in our system. However, in order to verify the blockchain's integrity, we actually need the complete chain of blocks. So in order to avoid any data from being overwritten, so what we do is we regularly export the blockchain data on the train nodes to external data centers of the railway companies. Similarly to how we share the authority over the juridical recording amongst multiple companies, we do the same with storage. So we can here consider either one data center of one railway company or multiple data centers of multiple companies. And we have one or more parties that sign off on the deletion, on the pruning of the blockchain data in order to give the ZugChain nodes basically a proof of pruning. The blockchain structure facilitates the export. We require 2 F+1 responses by the ZugChain nodes to get at least one correct response, as these nodes can behave Byzantine. And here we leverage the checkpointing subprotocol of the Byzantine agreement to verify the blockchain's integrity. The export protocol consists of the following steps. We have our ZugChain nodes on the train and the data centers. One data center can now query the ZugChain nodes for more recording data by sending a read operation together with the sequence number of the last successfully exported block, and then it waits for 2 F+1 responses. One ZugChain node sends all created blocks between this last exported block and the last block included in a stable checkpoint together with that stable checkpoint. A stable checkpoint in our Byzantine Agreement protocol includes the signatures of 2 F+1 replicas, confirming that they too have committed this block. So even if only one of these 2 F+1 responses actually reaches the data center, it allows it to have a quorum of signatures of the replicas on this block. And the other nodes as well respond with the last stable checkpoint. The data centers then synchronize the response amongst each other, verify it, and if the verification is successful, they create a delete operation up to the last block's sequence number, sign it, and return it to the ZugChain nodes. The ZugChain nodes then prune the blockchain up to this point and conclude the export with an acknowledgement. We have built a testbed out of real train hardware to evaluate ZugChain's performance. As shown on the right, we can see the 4 MCOM machines, which act as the ZugChain nodes. They are each equipped with a quad-core CPU, 2 GB of RAM, and are connected with a 100 megabit per second Ethernet connection and a bus connection using the Multifunction Vehicle Bus, the MVB, and they're all running a custom Linux kernel. The bus communication is regulated by the MVB master, and signals to be logged are generated by the DDC. We compare our communication layer with pure PBFT, which we consider the naive baseline approach to evaluate the effect of the filtering. Each request in PBFT is ordered, including duplicates, leading to requests being logged up to 4 times. For the measurements, we vary the bus cycle time, so how frequent and after how long we receive new data from the bus, and the payload size of the requests. As a bit of background on the multifunction vehicle bus, it is a field bus used by Siemens and ABB and is one of, if not the most widespread bus system used in modern trains. It offers synchronized leader-follower communication, where the bus master controls the cycle time and polls the connected devices for data, and we have 3 types of data that are transmitted via the MVB: process data, message data, and supervisory data. For juridical logging, the focus lies on periodically transmitted process data. As in our model, the MVB communication can contain transmission errors, for example, bit flips, leading to this diverging input that we receive on the ZugChain nodes. And we use the MVB in our prototype, but our design is independent from the underlying concrete bus system. In this plot, we show the network utilization and the latency of ZugChain compared to PBFT. On the left, we vary the bus cycle time for a fixed payload size of 1 kilobyte, and on the right, we vary the payload size with a fixed bus cycle time of 64 milliseconds. The network utilization of both measurements is higher for PBFT, as we have to order more requests, namely all the duplicates. Therefore, ZugChain requires less bandwidth of the potentially shared Ethernet connection. For the latency, we can see the difference as well, where ZugChain offers lower, more stable latencies. Note that the plot on the left is in log scale, and for small bus cycles, our system cannot handle the load of timely ordering these duplicates. Here we can see the measurements for the CPU and memory utilization for the same settings as before. ZugChain uses approximately 1/4 of the CPU resources of the PBFT baseline and also requires less memory. Especially again for lower bus cycles, we can see the large memory usage of PBFT due to the buffering of consensus messages. We can therefore conclude that ZugChain is better suited for usage on shared resource-constrained devices compared to an approach without filtering. Next, we evaluate the export protocol, where we export data corresponding to approximately 5 minutes of recording, namely 500 blocks, up to 3 hours with 16,000 blocks. We export the blocks via LTE to an AWS VM in our region. The export is split into the read operation, meaning from the data center polling the blocks up until the reception of 2 F+1 responses, the verification of the blockchain, and the delete operation, so from sending the signed delete message until the acknowledgements have been received. We can see that the verification is negligible and most time is spent waiting for the full blocks. 500 blocks are exported in about 5 seconds, and even for 16,000 blocks, the export lasts under 3 minutes. The continuous export is therefore feasible, and even if it is disrupted, for example due to mobile network availability, we can still export during train stops. 3 minutes of train stops for 3 hours of operation is acceptable. In our paper, you can find more evaluation comparing the view change performance and the performance under the presence of Byzantine faults. We have presented ZugChain, a blockchain-based juridical data recorder for railway systems, which is the next step in the digitalization of railway operations. Our design maintains the reliability and availability levels of the traditional JRU, while allowing the external verification of data integrity by using blockchains, for example after crashes and even with only one remaining record. We present an easy data export protocol to the data centers of railway companies, and our measurements have shown that our communication layer ensures good performance on real train hardware due to its efficient filtering of duplicates. With this, I'd like to thank you for your attention, and if you have any questions, feel free to send us an email. Thank you!